Today, I'm talking about rethinking interpretable machine learning for audio. My name is Vinod, and I recently defended my thesis. I did my PhD at Queen Mary University in the Center for Digital Music, and I was advised by Mark Sandler and Emmanuel Benetos. To kind of go over the structure of the presentation, I'm going to start off by explaining interpretable machine learning, because there are a lot of interesting challenges. And when I started getting into the field, even explaining or understanding what it was a little bit tricky. So I wanted to set up that because so we are all on the same page. And then what I want to do is explain a little bit about audio classification task and what a typical deep learning model for audio looks like. And finally, once we have that little bit of background, then explain why interpretable machine learning needs to be rethought for audio. So first is, why should you care about interpretability? And I think the easiest answer is, if you can interpret a deep learning model as a researcher, you might be able to understand when your model is making mistakes, and you can debug it and create better systems. And kind of this sort of leads into the fact that typically when we create models, we're usually measuring a single metric like accuracy, AUROC, something like that. But that often doesn't give you a complete picture of how the model is behaving. You can have 90% accuracy, but maybe you're interested in the performance of a particular class, and that has only 50% accuracy, whereas your other 5 classes has 95%. And this metric doesn't explain why that's the case or how to alleviate it. So I think interpretability can give a sense of how reliable a model is, and this kind of maybe explaining the variance in behavior. And what we have also seen in recent years is that machine learning models propagate a lot of harm if you're not careful. There's a lot of instances where you've seen that machine learning systems can be racist, machine learning systems can be misogynistic. And I think it's ultimately the responsibility of the people who are creating these machine learning systems, whose responsibility it is to mitigate this before it's deployed for public use. And I think interpretability could be an important tool in helping researchers identify these issues with their machine learning models before deployment. And finally, curiosity. I come from a signal processing field where I'm used to having like a concrete understanding of the signal path from start to end. And moving into the deep learning era, it's kind of been fascinating that there's so much of it that I don't understand, or a lot of my preconceived notions have been challenged by the ways that machine learning models I've worked with have behaved. So I just want to understand why that is. Interpretability I found was difficult to define. It first of all goes by different names. Some people call it interpretable machine learning. You have explainable AI, you have explainability, and there's this various definitions as well. But I think my favorite one is by Murdoch, where they define interpretable machine learning as the extraction of relevant knowledge from a machine learning model concerning relationship either contained in data or learned by the model. Here we view knowledge as being relevant if it provides insight for a particular audience into a chosen problem. Why I like this definition is that it explicitly takes into account the fact that knowledge is what is relevant for a particular audience. Because if you, let's say you want to explain how a music app recommends songs, and the information that is relevant or to a user is different from what might be relevant and important to a musician, is different from what is relevant and important to an artist. And I think this definition sort of includes that. I didn't find and I think that's an important aspect of interpretability. For the rest of this talk, mostly talking about gradient-based interpretability methods. Gradient-based interpretability methods are post hoc, which means they're computed after the model is trained. They're local, which means that It provides an explanation for a particular input, not a general explanation of the model behavior. And the only requirement is that you can compute a gradient for the machine learning model. So one of the most popular gradient-based interpretability methods is saliency maps. And this is kind of typical examples of what you would see for saliency maps in computer vision and natural language processing. So on top, you have MNIST, where on the left you have the image, and on the right you have the saliency map, which kind of suggests that in order for the model to predict that the output is 1, it's focusing on pixels that are basically the white pixels in the image, which intuitively makes sense, even though I'm someone who's not necessarily worked a lot with computer vision. Similarly, with natural language processing, a model is performing sentiment analysis, and it's showing the saliency map with respect to the embedding vectors. And here for the sentence, "I hate the movie," the word hate is the one that the model relies on most in order to predict the sentiment. Again, just intuitively, just through knowing English and having some basics of deep learning, I can make this connection that, okay, maybe hate is important for the model. So that irrespective of, later on, we'll get into the unreliability of saliency maps, but what is convenient about saliency maps and things like that in computer vision and natural language processing is it's very easy for me to understand discussions about what is happening because it is presented in a manner that's easily understandable. But when it comes to audio, it's a little bit different. And to start, it's about how inputs to audio classification learning systems are. So typically audio is stored in the form of a waveform, and a waveform is just a way to capture the way that a sound wave is propagated. So it has properties like the amplitude, which is how loud the signal is, frequency. And in this case, it's showing a sine tone, which is maybe slightly easy to interpret, but a typical waveform is going to be much more complicated and hard to understand what exactly is the content of the signal just by looking at it. You'd need to listen to it. And typically waveforms are converted into some sort of a time frequency representation. So here, as an example, I'm showing a magnitude spectrogram. And what a magnitude spectrogram does is it shows the frequency content of the signal. So not only do you get the general energy level across time, it also tells you which particular frequencies are important. So in this signal, in the beginning, there are some, so it gives you like harmonics and things like that. And magnitude spectrogram is not the only type of time frequency representation. There's a lot that's used in audio classification systems, and there's no standardization. There's different hyperparameters that goes into it, and there's not like, this is the standard format that everybody uses. So this makes it tricky because saliency maps on spectrograms are difficult to standardize because so this is just an example of a spectrogram on the left and what the saliency map for it looks on the right. And this is for singing voice detection. And you can see like faint lines of harmonics over here, but it's very faint. And unless I knew based on the label that singing voice was present in the signal, it would be difficult for me to actually know that singing voice actually, that this was an audio clip that contains singing voice. And the saliency map doesn't necessarily correlate to my kind of assumptions of what singing voice should be like. So in a case like this, the saliency map doesn't really help in providing information the same way that it did for computer vision and NLP. And for the raw waveform, there is almost no work that has, there's a little bit, but there's no general consensus on how to even generate a saliency map for a one-dimensional vector like this. Maybe in the best case scenario, it'll give you regions which are important for the model prediction, but maybe that's the maximum amount of information you can get from just using a saliency map on a raw waveform. And maybe the best solution is, because we need audio solutions for an audio problem. And one thing that we did try was borrowing masking techniques from source separation. So in the previous example before, you have a saliency map like this, and you can convert it into some sort of a binary mask, and then mask the spectrogram, and then try and invert the spectrogram into a raw audio waveform. And then maybe by listening to it, it will filter out, the unimportant sections and leave behind the important sections, and you can actually listen to what is important for the model. But this is tricky. In practice, there is a lot of decision-making process. Like when you're generating a binary mask, do you ignore, how do you take care of the signs of the saliency maps can have positive and negative values? Do you ignore the signs? Do you only take the positive values? Do you only take the negative values? What percentage of the spectrogram are you masking? Is it 10, 20, 30, 40? And we tried different permutations, and when we were listening to the examples, we weren't really getting the type of results we wanted. And there was no, it was not easy to come up with a methodology to refine this process. So it was a little bit of a dead end. And the other thing to take into account is a lot of these time frequency representations are not invertible. So there's noise introduced by inverting the spectrogram back into the raw audio form. So to summarize the challenges, in audio, the inputs are not as intuitively interpretable as in computer vision and NLP. And we don't really know whether we need to be coming up with different techniques for the different audio representation, input representations in audio. And oralization, which sounds like a nice romantic solution, is trickier than we anticipated. And generally, one thing that we look at is, even if we solve these issues, what does a visualization exactly mean? Like if we go back to this image of MNIST, which of these pixels are actually important? And that's unclear. So that is kind of the main question that we are trying to, so I feel like that is something that is unclear from saliency maps in general, or a lot of gradient-based interpretability methods. So my approach was to just focus on, and I'm going to keep this brief because there's a lot of details. What we try to do is just focusing on understanding what a saliency map means, because there's the magnitude, the signs of the saliency map, and various ways in which you can compute a saliency map. And we decided to come up with a quantitative approach to evaluate what the saliency map meant. So what we did was, similar to the oralization process, we created a binary mask from the saliency map by ranking the values in different ways, and we applied these masks to the input. And the idea was that if the saliency map was highlighting important features, then the mask would remove the important features from the input, and the model performance should decrease. And similarly, if the saliency map was highlighting unimportant features, then the model performance would remain the same. In general, the results we found was that for a task like MNIST, we can mask up to 782. So we reduce it to a simple problem of classifying between 0 and 1. We can mask up to 782 out of 784 pixels and still maintain 100% accuracy. And visualizing it, we were able to show that the model is just looking at central pixels for 1, corner pixels for white. And for singing voice detection, we can mask up to 98% of the log-mel spectrogram and still maintain an ROC, AUROC above 0.99. Finally, what I want to say from this is, there's a lot of unexplored area, especially in the area of audio and interpretable machine learning. And I feel like almost a lot of the questions that I had as a fall, during my PhD could lead to another PhD on its own. And there are probably like 10 people working on this problem in the world. So I feel like any kind of work that's done in this area has a potential for strong impact in the community, and you can be a pioneer in the field. And I got into this field because I heard a PhD student do a presentation at a conference. hopefully this inspires someone to take up this topic in a similar way. Thank you.